about this equivariant spectral sequence for TMF2, and all of this is joint work with Jeremy Han, Andrew Sanger, and Falling So. So before sort of an immediate application of the things I'm going to talk about is a computation of the three localized homotopy group of TMF using algebraic method. And before I jump into what the spectral sequence is, maybe let's just briefly review what TMF is. So TMF is a short name for topological modular forms. It's constructed by Gorz-Hopkins-Mellor and reconstructed by Lurie. And one of the main features is that it's a connective infinity ring spectrum. And roughly, it represents the universal elliptic cohomology theory in the sense that, well, it can be obtained as the homotopy limit of elliptic spectra over some compactified modular stack. And as a result, we expect that, well, it should contain some height 2 information because elliptic cohomology theories are height 1 or height 2. So in particular, its homotopy group should know about V1 and V2. And of course, the homotopy group of TMF was well studied. And there were unpublished computations by Hopkins and Mahowitz, and they were written down by Bauer, and there are many other approaches to compute pi star of TMF. So some of the interesting things about this is that if we consider the unit map into TMF, and we take homotopy, then this sort of detects order torsion in TMF, and there are only 2 and 3 torsions. So in a small range, pi star of TMF is actually a pretty good approximation of homotopy group of the sphere spectrum. On the other hand, there's a ring homomorphism to the classical ring of modular forms, and this is almost an iso on non-torsion elements. So the homotopy group of TMF is sort of made up of, torsions seen from the sphere spectrum and some interesting information about modular forms. So yeah, in previous methods, all require topological inputs. To name a few, there's the elliptic spectral sequence. There's atom spectral sequence, rather than atom spectral sequence, maybe by Dominic Culver, Mike Hill. Elliptic spectral sequence was probably what the original approach was. And there was the homotopy fixed point spectral sequence that was implicit in the work of Hopkins, Hill, Ravenel, and recently written down explicitly by Angelini, Mark Behrens, Eva Beaumont, and Hannah Kohn. And all of these require some sort of, either information about the sphere spectrum, homotopy group, the sphere spectrum, in a sense that, well, we need to push forward some differentials in the Adams-Novikov spectral sequence, converging to a computing sphere spectrum, and maybe some sort of power operations or some sort of total bracket. So these are all informations or tools that, require some homotopy theory input, or in other words, it cannot be deduced merely by knowing the E1 page, the chain complex on the E1 page, and the D1 differentials. So the point of this talk is that we'll explain how to compute pi star, this free localized homotopy group of TMF, using an entirely algebraic method. And the input we use here is the C3 equivariant two-Singer algebra. So first, let's just do some reduction. So let's just assume that everything is relocal. So relocal from here on. Yeah, you can see that, my handwriting in real time is pretty messy, but it's going to be better than Tomer's.
That's a high bar.
Exactly. So free locally, TMF is the genuine sigma 3 fixed point of TMF2. So again, we don't really need to know what TMF2 is. It's a genuine connective E-infinity ring spectrum with a genuine sigma 3 action. And as a result, the three local homotopy group of TMF can be obtained by first taking the C3 homotopy group of TMF2, and then we take the sigma 2 fixed point because it's free local. And this sigma 2 fixed point here turns out to be very easy to understand. So we reduce the computation to understanding the C3 homotopy group of TMF2. And while genuine fixed points are usually hard to work with, so let's use the standard trick, which is the Tate diagram. We decompose TMF2 and the genuine C3 fixed points into the geometric fixed points, homotopy fixed points, and the Tate construction. And the geometric fixed points turns out to split into a wedge of suspensions of F3s. So this is F3 on a polynomial generator Y in degree 6. And Tate is further inverting Y. And this is a pullback diagram. Therefore, if we want to compute homotopy group of the left of this corner here, once we know what the homotopy group of the homotopy fixed point is, then it's again going to be very straightforward. So we reduce to pi star on TMF2 and then take homotopy fixed point. Well, there is another way to express this. This is the integrated part of the C3 homotopy group of TMF2, but Borel-ified. Well, why is that so? Borel-ification is mapping from C3 plus into TMF2, and taking the C3 homotopy group is precisely computing the homotopy group of the homotopy fixed points of TMF.
Excuse me, what is the dimension of that Y?
It's in dimension 6.
Thank you.
And also, when you're writing F3 for HF3 for the Eilenberg-MacLane spectrum.
Oh, yes, exactly. So yeah, you're going to see many bad notations. So I'm going to write essentially everything you see as F3 or F3 underline, and it can mean many things. I will try to be consistent. So here it actually means HF3. Yeah. Okay. So yeah, before we jump into the order of the alt prime, let's just do the warm up where p is equal to 2. And here the analog is KUR, whose C2 fixed point is little ko. If we take the Borel-ified KUR, then this is true only in the negative homotopy groups, but this is exactly what we care about, right? So there's an obvious thing to do here, which is the homotopy fixed point spectral sequence. And this is probably the first example in any computational equivariant homotopy theory course. So homotopy fixed point spectral sequence goes from the group cohomology, the C2 group cohomology with coefficients in homotopy group of Ku, and converges to the homotopy group of the homotopy fixed point of Ku, which is C2 homotopy group of KUR Borel-ified. So there are non-trivial D3 differentials that are deduced either from an Adams-Novikov spectral sequence or some geometric methods. So this is some non-trivial differential. That's not a D1. And on the other hand, we can try to use the C2 equivariant Adams spectral sequence for KURH. It has E2 page, this X group over the C2 homotopy group of F2 underline tensor F2 underline over KU. And as you expected, here it's really H here, but yeah. So what is this? So this thing here is a Hopf algebroid. It has another name, E1R. Okay. It's a pretty small Hopf algebroid given by F2 underline adjoining polynomial generator tau 0 and tau 1, subject to relation that tau 1 squared is 0 and tau 0 squared minus 8 tau 1 is 0. So this is a quotient Hopf algebroid of the C2 equivariant dual singlet algebra. Which is F2 underline tensor F2 underline. Sorry, pi star. Okay, let me just pi star C2 F2 underline tensor F2 underline over the sphere spectrum. And this was computed by Wu and Krish. So this thing here is flat over the coefficients. And as a quotient, this is also flat. That's why we're allowed to write the E2 page as an X group over hop algebraic. So there is a single non-trivial right unit on U sigma. U sigma is sent to U sigma minus tau 0 A sigma. And now we do the standard trick, which is called the equivariant May spectral sequence. So May spectral sequence, or in other words, it's really the algebraic a sigma box sign spectral sequence. So we filter away the right unit by filtering the cochain complex by powers of a sigma, sorry. And in this spectral sequence, we can detect the D3 differential that's in homotopy Higgs point spectral sequence. And any hard differentials in the A-spol box sign spectral sequence becomes a D1 differential in the atom spectral sequence. Therefore, the key point is homotopy Higgs point spectral sequence D3 upwards. It becomes an Adams D1. And after that, after we run this D1 differential, there are no space for more differentials. So the spectral sequence collapses on E2. And we're done.
When in the formula for A to R, you wrote a minus sign. I just want to make sure that we're working mod 2 here, right? So minus is, I mean, it's okay to write minus, but minus is plus here, right?
Yeah, it's a plus. Sorry. Yes, that's totally right. Yes. Yeah. So in some sense, so that in this well-known case, the C2 equivariant atom spectral sequence is pretty smart. It doesn't have any hard differentials. Somehow knowing the hop algebraic is enough to deduce the entire spectral sequence. And in fact, the atom spectral sequence for BPR collapses on E2. This is again, it was proved in Hu and Krish and further exploited by Li, Shi, Wang, and Xu. So and one name for, so we've been studying KUR here. Another name for KUR is BP1R, right? So it's the beginning of a series of truncations of BPR. And here, TMF2 is BP1 mu P. Again, sorry, BP1 mu 3. So if the conjectural BP mu 3 exists, then TMF2 is the one truncation of that spectrum. And this is shown by Dillon-Wilson. So it's reasonable to expect that the same method we've been using to compute pi C2 homotopy group of KUR should also be, an efficient way to compute something like TMF2 at prime equal to 3. All right, so equals to 3, the C3, we can use the C3 equivariant relative atom spectral sequence, also known as the descent spectral sequence, along TMF2 mapping to F3 underline. And let's just, for convenience, assume that everything is Borel from here on, so I will stop writing the little h. So the E2 page is the homology of the cochain complex given by C3 homotopy of F3 underline. This right minus left unit mapping into C3 homotopy of F3 underline tensor F3 underline over TMF2. There's some phase maps. Yeah, you know the idea. And this converges to the C3 homotopy group of TMF2. So immediately we're starting to notice some problems. So this second term here, in the case k equals to 2, this is a nice half algebraic. So what is this thing here at prime equal to 3? So C3 homotopy group of F3 underline tensor F3 underline over TMF2. This is F3 underline adjoining tau 0. So it's modular over F3 adjoining a exterior generator on free spheres S0, S0 minus folk, and S4 rho minus lambda. So what is this spoke here? The spoke is the one skeleton of S rho, S lambda, sorry, S lambda. It's the inclusion of the one skeleton. It can also be obtained by mapping C3 plus into S0 and take the core fiber. So unfortunately, so S spoke, this is not a Picard element. So therefore, if we want to work with spoke-rated homotopy group, we really have to be careful. So for instance, if we want to say, so spoke looks like it's half of lambda sphere, but it's not technically true. So if we call this a spoke, and we call the inclusion also a spoke, so these are two different maps, so, but we just kind of keep track of where we are mapping from, then we can say that a spoke square is a lambda, but it's not, true, like literally true. So, and suspend, so this homotopy group over here, this is not flat in a sense that it is not just ROC3 graded suspension. We have this spoke graded suspension. This is sort of bad news because we cannot just rewrite the EG page as an X group over a half algebraic. However, there's some saving grace. So modulo the image.
Excuse me, Adela, what do you mean by 2 rho minus spoke? What does that mean?
Okay, so minus spoke is so S minus spoke is the spanning one half dual of S spoke.
Okay. Okay.
But it's not because element means that, so if we tensor these two together, this actually it splits non-canonically as S0 plus a C3 plus. So there's a free part here that's causing all the problem. And in fact, as the next proposition,
so wait, is that dual just a desuspension of S spoke?
Desuspension, yeah. So S lambda tensor S minus spoke is S spoke. So they're related, but they're not literally just inverse of each other. It's not invertible.
Okay.
Yeah. Okay. Yeah. So there's this free thing that's really annoying. It causes so as a result there will be transfers in the homotopy groups. But modulo the image of transfers, modulo the free things, the C3 homotopy group of F3 tensor F3 over TMF2, it is a half algebraic. So if we work modulo transfer, things are much nicer. So explicitly, so if the spoke graded homotopy group of F3 underline, this is normal F3 on two polynomial generator A spoke, U lambda plus minus, and there's an exterior generator U spoke. This is a refinement of the usual ROC3 graded homotopy in a sense that so epsilon is A spoke, U spoke, and A lambda is A spoke square. Again, it's in the sense that we're defining here, these two A spoke are definitely different from each other. And so the spoke graded homotopy of F3 tensor F3 underlying over TMF2. So it's this thing. So this is the nice part. This is the A spoke torsion free part. And this part is the torsion part. It sort of comes from this free part of the spoke sphere. And the right unit on U spoke is U spoke plus A spoke tau 0. And the right unit on U lambda is U lambda minus A spoke to the 5th tau 1 mu 3. So tau 1 mu 3 is this element living inside the half algebraic. And as we'll see later, these two right units, so in the P equals to 2 case, we saw that the right unit tells us about the D3 differential in the homotopy fixed point spectral sequence. And here we will see that, so it will tell us about the D5 and D9 differentials in homotopy fixed point spectral sequence for TMF2. So how do we deduce these right differentials? well, in fact, recently, a while ago, Hu, Krish, Sundberg, and Zhou, they computed the right-left unit and co-product on the C3, the ROC3 graded. This is not the spoke grade. ROC3 graded homotopy of F3 tensor F3 underlined over the series spectrum. So this is the C3 equivariant dual singular algebra. And there's a map to C3 homotopy of F3 tensor F3 over TMF2. That's almost objective. It almost hits everything. And from their results, we were able to deduce all the right units, left unit, and co-product. And of course, and just to mention, so this object here, without the structure maps, these were first computed by Stenker and Wilson. And in their computation, we can already see that this is not flat because it's split. So there are some two cell complexes in this that just it does not just split as suspensions of ROC3 graded suspensions of HF3s. Okay, so now I can finally state the key point. So the key point is that the C3 equivariant relative atom spectral sequence for TMF2, this is completely determined by the co-chain complex of Mackey functors. So here I'm showing you the E1 page of the relative atom spectral sequence along with the differentials. So what I'm allowed to do is I'm allowed to copy paste to get the Mackey functor. We want to change C3 into underlying. So there are transfers and restrictions between these things. And the bottom complex is the Kobar complex computing the relative atom spectral sequence for the underlying TMF2. So more precisely, so we don't even need to know everything in this picture that I'm drawing here. So for instance, we don't really need to know the restriction map here. We haven't really tried to compute all the differentials upstairs. We only kind of computed mod transfer. So more precisely, what we're using are the two following inputs. We know the Hop algebraic structure on pi star C3 homotopy group of F3 tensor F3 underline over TMF2 mod transfer. This was in the proposition I showed earlier. We also need to know the homotopy group underlying homotopy group of F3 underline tensor F3 underline over TMF2. Well, this is the same as the homotopy group of pi star of F3 tensor F3 over TMF2, but also recording this the C3 action on it. So this we know from a result of Stoyanovska. Stoyanovska she shows that this homotopy group here is C3 adjoining polynomial generators sigma lambda 1 and sigma lambda 2. And equivariantly, this is sim over C3 on rho bar in degree 5. Okay. So this is all we need. And so both of these can be considered as algebraic information. And the theorem is the following. Relative atom spectral sequence for TMF2, the C3 equivariant one, it actually collapses on E12. So there are many higher differentials, but the higher differentials are determined for tri-degree reasons, and the degeneration of the spectral sequence at E12 is also for tri-degree reasons. So I will explain what tri-degree means. So we're just, instead of just the atoms filtration, we need to keep track of another filtration. So that's what I mean by a tri-degree. So we need a bifiltration on TMF2. And so again, I want to stress, so even though, unlike the case P equals to 2, this spectral sequence does not just collapse on E2 page. So usually when people say that the spectral sequence degenerates for degree reasons, they mean that on E2 page, there are no rooms for differentials, we're done. But here, we can also say that it degenerates for degree reasons, but there are higher differentials. It's just that we can deduce it by completely formal or algebraic arguments. And before I start telling you about how we compute this, let's just see some charts. So this is the E2 page of the relative atom spectral sequence for TMF2. As you can see at the beginning, there are no room for differentials. Very good. So there are a bunch of things along the top. These are all transfer classes. So the little arrow on top, these means that there is a 3 extension. So there are a bunch of things, and as you can see, as we go further and further into the stems, there are a lot of things that need to disappear, right? So the final answer is pretty small. But the pattern wasn't too bad. So there are a bunch of white dots on the bottom line, and there are some black dots. Yeah, I'll try to explain this later. So there are 2 patterns of differentials. So the bottom white dots, a lot of them kind of support differentials into the black dots. These are periodic after they kind of stabilize this to a periodic pattern, and the longest that these differential can be is I think it's a D10. And after these differentials happen, so suppose that these differentials happen, so we're left with a bunch of other things that can potentially support differentials. So I marked out all these green dots, which are the spots that could support differentials, higher differentials. And in fact, they all do support differentials. So there are D5s and D6 and D11s happening that wipe these green dots out. And after these 2 types of differentials happen, there can be no room for differentials. So this is the E12 page. So as and maybe let me just note that this pattern stabilizes after 144. So starting from 144, everything is concentrated in this band of slope of 4th. And so say it's 36.9 periodic. It's in Adams grading. And yeah, it is kind of an interesting phenomenon because, as I mentioned earlier in the talk, TMF itself should detect V1, V2. So it should detect height 1 and height 2 information. So in a classical atom spectral sequence for TMF, we know that the final result sort of lies within 2 bands. There is, so by essentially, I mean that I'm just ignoring all the 3 extensions from the transfer classes. But in classically, there's a slope of a 4th, and there's a slope of 1/16 that's given by V2 to the 9th. But here, everything just stays in the same band. So it almost looks like it's height 1. And this is, again, not, too surprising in the sense that, TMF2, right? We've been saying that TMF2 is a form of EP1 mu3. So equivariantly, it does look like a height 1 thing. And, its homotopy group, it's polynomial on one single generator if you think equivariantly. Okay.
So can I ask, so I not familiar with like the value, the number values at odd primes. So but this 1/4, that's the slope of V1 in this P = 3 context. Is that right? Okay. And are these is it actually V1 periodic in some sense, or just?
I won't say so. So I mean, V1 is in some sense alpha, right? But alpha is an exterior class.
Oh, I see. Okay.
Yeah. So I mean, again, one thing that we do not. So if you really want to say it's periodic, it's periodic on this class here that we are not naming. We do not. So the atom spectral sequence is not great for multiplicative structures, unfortunately. But if you want to say it's what is periodic on, it's periodic on this class, which I can give you a name, but it has some hidden lambda.
What stem is it in?
36.9.
Okay, got it.
Yeah. Okay. So now hopefully I've convinced you that there's something interesting going on. So now let's see what's the strategy here. So how do we deduce all these green differentials and gray differentials, higher differentials without using any topological methods? The strategy is that we're using a bifiltration. So we construct a bifiltration on TMF2 as follows. So this is the usual descent diagram along TMF2 mapping to F3. So what we're first going to do is that let's take level-wise whitehead filtration. The whitehead, we apply the level-wise whitehead tower to this co-simplicial diagram. Therefore, we get so this is a co-simplicial object. In SPBC3 field. So this is the category of Borel C3 equivariant spectrum, and this is the category of filtered object. So we can consider a co-simplicial object in this filtered category. And then let's use the infinity categorical dot-con correspondence. So we kind of transform this co-simplicial object into a filtered object in here. Therefore, it requires a bifiltration. So as a result, we get a bifiltered object, which I just denoted by whitehead atoms. So whitehead is the direction of the whitehead tower, and atoms is the direction that comes from this infinity category called correspondence. So this is the bifiltration. And once we have a bifiltration, we have a notion of trigraded homotopy groups. So the three gradings are whitehead filtration, Adams filtration, and the topological degree. And given any bifiltered object, we get a square of spectral sequence. So the associated square of spectral sequence is the following. So on the one hand, we can kind of collapse the whitehead's direction first. So this is going this way. This is the A-spoke box sign spectral sequence. So this is where we filter away the right unit, and then the hard differentials will be deduced by the right unit. And then we collapse the Adams filtration. So this is the relative Adams spectral sequence. On the other hand, so the other direction is we fold the Adams direction first, and we fold the whitehead direction. So an interesting feature here is that this, in fact, is not the homotopy fixed point spectral sequence. It looks very much like so. It has the same E2 page. It has the same E infinity page, and in fact, the picture looks very, very much similar to each other. But the filtration is slightly different. This is because whitehead tower it's not an exact functor, so it does not pull out the totalization. So there is a very subtle filtration difference between this top spectral sequence and the homotopy fixed point spectral sequence. Yeah. Okay, so now let me.
Sorry, I keep interrupting, but I hope that these questions are relevant. Okay. You've been referring to the relative atom spectral sequence. Can you just say a few words like why is it not just an atom spectral sequence? What do you mean by the relative adjective?
The relative is the one that's associated to this diagram. Maybe it's just called atoms. I mean,
it's fine. It's your talk. You can call it whatever you want. I just wanted. I was just wanted to understand what it was. Okay.
Sure.
And that's it for now. Sorry.
No, go ahead. I always talk too fast, so please interrupt me so I can slow down.
Well, this is sort of a bigger question, maybe let's for the end, but when you're doing these truncations to this Adams resolution, that looks very similar to the kind of things you do like with, synthetic technology.
Yes, exactly. So yeah, so it ended up being very synthetic rather than equivariant. Yeah, so the plan is basically we need to figure out how the differentials, so this is actually called the coherent spectral sequence in a sense that, well, for some stupid reasons, but so we can deduce we can completely determine these two corners, these two legs, very algebraically. Just like it's pretty easy, it's straightforward, all the hard differentials. But in order to sort of push forward the differentials here to the atom spectral sequence, we really need to use synthetic methods and very heavy synthetic methods in this bifiltered category. but I probably won't have time to get into it, but maybe, yeah. So maybe let's first explain more precisely what's this A4 box sign spectral sequence, or also known as equivariant May spectral sequence. So yeah, so this is the E2 page of the atom spectral sequence, homology of this Cochin complex with some non-trivial differentials in it, and the right unit is given by these two things. So the A4 box sign spectral sequence is obtained by filtering away the right unit. So the E1 page, of the A4 box sign spectral sequence would just be again the same thing here, but with simplified differentials. So yeah, so it's kind of simpler. But again, it's still very difficult to compute directly because because this thing here is only a Hopf algebraic mod transfer. We cannot write the A4 box signs E1 page as X group over a Hopf algebraic, and so we need to use some other tricks to compute this. So let's see bullet be the Cochin complex of the Kobar complex of the underlying TMF2. So this is the Kobar complex, computing the atom spectral sequence for pi star F3 tensor F3 over TMF2. So this is a discrete Cochin complex. So this lives in so the heart of this infinite carry of Cochin complex in this Borel's C3 Borel F3 modules. And one thing we can do is that, well, we can just see that, well, because everything is Borel here, so pi C3 homotopy group of F3 is really the homotopy group of F3, and then I take homotopy fixed point. So similarly, everything here. So I can rewrite the E1 page of the A4 box sign spectral sequence as this. And then what we can do to the C bullet thing is that we can take level-wise homotopy fixed point. And what we get now is an object, it's no longer a discrete thing, it's just an object, a coherent Cochin complex in F3 modules, right? So coherent Cochin complex means that I have a Cochin complex, but they're connected by null homotopies, and there are coherent conditions among these null homotopies that sort of record the higher differentials. And we can just observe that now in fact the E1 page of the A4 box and sequence is actually the E2 page of the spectral sequence for this coherent Cochin complex. So a coherent Cochin complex is the same as a filtered object. So with a filtered object, you have an associated spectral sequence. And because the A4 box sign E1 page is literally just taking homotopy group of this level-wise thing. So this is the same as the E2 page of the spectral sequence for this filtered object. And so we can try to compute the E1 page now by actually computing the right leg first. So the right leg we actually have a better handle on. This is because this coherent object, it lives in a fiber sequence. So we can first take level-wise transfer of the C bullet, and the co-fiber of this is the co-connective Tate. And so transfers, these are all discrete. So it's actually it's a coherent Cochin complex, but it's actually a discrete coherent Cochin complex. So the spectral sequence for this thing actually collapses on E2. On the other hand, so this coherent Cochin complex, it also has the spectral sequence collapsing on E2. And the E2 is given by X group over this little algebraic modular transfer. Because taking Tate is like inverting A sigma. And in this world, A sigma torsion is the same as being a transfer element. So by going to Tate, co-connect with Tate, what we're doing is modeling out transfer. So what we get is, in fact, a cobar complex for a Hopf algebraic. So we know how to compute the E2 page as an X group over Hopf algebraic, and just for sparsity reasons, and because it's Tate, this actually collapses on E2 page. So we re-express this coherent cochain complex C-bullet HC3 as two things that have spectral sequences that collapse on E2 page. And furthermore, we know what the spectral sequence for C-bullet HC3 converges to. So this converges to the homotopy group, the C3 group cohomology of 3 graded of pi star of TMF2, right? So this, again, we know very well, this is just sim over F3 of rho bar in some suitable suspension. So we know what the final answer should be. We know we know the fiber sequence when it's sitting inside. So we can just deduce the differentials by finding specific resolutions for every representation that lives in sim F3 rho bar and matches it with things that live in both sides. So as a result, basically for any representation that's living in here, for any representation, if rho bar is living in here, what you will see is that so this spectral sequence is sort of weight graded, and all of these representations they live in a unique grading. So for each of this, there will be something that comes from Tate that lives along a line. So these are the white dots that we've been seeing on the in the Adams chart. And there will be a bunch of things that come from transfer classes. And so the higher differentials in the coherent spectral sequence will be something like this. Okay, I'm not drawing it correctly. There are some zeros here. But it can be completely determined just by picking a resolution for each of these representations that we're seeing showing up in the final answer. And maybe it's time to go back to the charts. So these are all what these gray classes do. So of course, these are not all the gray classes, because what's happening is that, of course, we hope that the A-spoke box sign differentials and all these differentials from the coherent spectral sequence will just naturally just don't interfere with each other. But in fact, that's not what happens. So what's happening is that some of the gray differentials coming from the coherent spectral sequence, they do live on to become atom spectral sequence. But some of these, their sources, the source of these differential, they participate in the A-spoke box sign spectral sequence. So this is where all the green dots come from. So these green dots, every pair represents a pair of differentials in the coherent spectral sequence, and the source of that pair of coherent spectral sequence, they actually support an A-spoke box sign A-spoke box sign differential, and their targets sort of just live on to the atom spectral sequence. So for instance, so this thing here that supports should support a D6 atoms differential. So the source of their coherent spectral sequence differential, they're killed by a D5 A-spoke box sign differential. So the D11 here, the D11 here comes from, again, a D10 A-spoke box sign spectral sequence interfering in the coherent spectral sequence. And it is in deducing these spectral sequence that we really have to use synthetic methods, because as you see, so at some point, maybe at some point, the sparsity argument can no longer work. Of course, we don't really want to just use the final answer to deduce anything, but even if we want to use sparsity argument, as you can see, like at some point, these parallel lines start wrapping around each other. So in the same degree, there might be many green dots when you go higher and higher. So even these gray differentials, we really need to consider, tau inverted lambda box sign spectral sequence or lambda inverted tau box sign spectral sequence. in the sense that we need to keep track of all the tau torsions and lambda torsions. Tau being the whitehead filtration parameter, and lambda is the LM spectral sequence parameter. Yeah, so, okay, I think my time is up, but yeah, that's it. Sorry.